the amount of heat that you add to the system to the change in temperature. And this is the relationship. The heat added, temperature, and this is a proportionality constant. This heat capacity depends on path. So here are two kinds of experiments. Here we have a fixed volume, and we have a little candle, and we're adding heat, and when we add heat, the pressure does what? It increases, and the temperature. Okay, this is MIT. You guys know something. You should yell it out, not just whisper it. You have the confidence. I mean, maybe up the street we whisper, but here we know it. And so here is a different kind of system where we have a constant external pressure. We add heat to the system. And so here the volume can change, the temperature can change, and so as we add heat here, the temperature goes up and the volume. That was even quieter than last time. Okay, but you know it, you understand it. Now, the coefficient that relates the amount of heat in to the temperature change is obviously going to be different for these two cases. In this case, where we have a fixed volume, we say dQ is equal to CV, heat capacity, dt, where the V specifies what's constant for the path. And so this is one path, constant volume. This has a particular value. Over here, we have dQ Cp dt. The heat, the proportionality between heat and temperature rise is given by this, the constant pressure heat capacity. They're different quantities. If we want to know the total heat added to the system, we can measure it, which is the straightforward thing, but sometimes you want to calculate it in advance, or sometimes you want to calculate it on an exam. So we do an integral over a path for the heat capacity along that path, dt. So for Cp and Cv, these are often quantities that are measured as a function of temperature, and one could, in fact, calculate this integral. For most problems on exams, those quantities are constant, independent of temperature. But there's no guarantee that they will be.